Hello everyone. So I will present to you our paper that is addressing the problem of optimal residential battery scheduling. And we aim to consider the assets lifespan into consideration and the battery depreciation especially. This is the work that was done with my colleague from Heriot-Watt, so University in Scotland, Edinburgh. So in terms of context, the context is that there is a Paris Agreement on which all the countries, and especially Western countries, agreed to decrease the carbon CO2 emissions from 32 kilogram per day to 5.5 kilogram per day. This means that we all need to increase the share of renewable energy into our consumption. And actually, some signs that do not go in the right directions are the reduction of feed-in tariffs. So the fact that money is given to small prosumers when they export electricity onto the grid. So that was quite convenient to give a business model to rooftop PV and small wind turbines. And now with the reduction of feed-in tariff, this is a new incentive for self-consumption. So with self-consumption, the thing is, rooftop PV is one of the most convenient distributed generation for residentials. And unfortunately, the PV doesn't produce at the time at which we consume, given the fact that most of our consumption is during the evening or night. So there has been a recent development of residential batteries, such as Tesla's batteries, LG, and other manufacturers. And with that development of batteries comes the question of control of batteries. So how do we optimally control those batteries in order to reduce the payback period of these assets? So in terms of controls, this will be the topic of this talk. Battery control algorithms are classified in two categories. The first one is the one that we see on screen at the moment. So the battery control algorithm takes as input real-time production, real-time demand, and the pricing, electricity pricing at the moment, and controls the battery in terms of charge, discharge, decision, and power in order to export or import to or from the grids. And another type of algorithm is what we call optimization-based algorithms. So those algorithms are using forecasts for production, forecasts for demand, and for electricity prices, provide an optimal scheduling of the battery charge and discharge. And this optimal schedule is sent to the real-time battery control algorithm. So those are the two types of control algorithm. And in this talk, we will address the problem of optimal scheduling algorithm. So in terms of optimization, it can be based on linear programming methods or evolutionary algorithm. And in this work, we only address the problem of linear programming optimization-based control algorithm. So in terms of literature review, the battery control topic is a well-studied field with many publications on the how to best schedule a battery. And one thing that we have to keep in mind is the fact that cycles of operation affect the lifetime of the battery. So here we can see a curve. So on the x-axis, we have the depth of discharge for each cycle. And on the y-axis, we have the number of cycles that are allowed in the lifetime. This is the black curve. And the equivalent is the linear curve. This is the inverse of the exponential-like black curve. So the blue curve is basically is the cost of one cycle depending on depth of discharge. So we see that basically when a battery discharge at full depth of discharge, then it will have a higher cost, meaning that the battery won't be able to handle too many cycles at full depth of discharge. So the question is, when we use batteries for self-consumption, where are we in the curve? How are cycles affecting the lifetime of the battery? So this is, and the big question is, do we have to include this consideration of the battery lifespan into the optimization formulation? So previous works have proposed some solutions in order to include the battery lifespan into the optimization problem. However, most of the works only work or only consider cycles that start at 100% of the state of charge and discharge the battery by a certain depth of discharge. However, when we consider batteries for electrical grid applications, then the depth of the state of charge at the very beginning of each cycle is not necessarily 100%. For example, a battery can discharge from 100% to 20% and charge again from 20% to 40%, and then discharge again from 40% to 10%. So this kind of operation requires to have an algorithm that considers the battery lifespan, including cycles that do not start at 100% of state of charge. And as I mentioned previously, we want to have a linear programming formulation in order to have something that will be solved quite quickly. So basically, conventional battery control optimization are, and especially those not considering, well, the basic one, not considering battery lifespan, they aim at minimizing the costs of operation or maximizing the revenues from the use of battery. So we usually achieve a mixed integral linear programming optimization problem where we minimize the energy import costs and we maximize the energy export revenues. And by doing that, we change the variable which is the schedule of the battery. So the charging or discharging power, the operation power for each of the time step of the operation. So if we have 24 hours, 1 hour time step for one day, then we will have a schedule of 24 elements in the vector that represent the battery power. So optimization variables are the power of the battery at every time step, as I just mentioned, which is basically a vector of 24 elements. And then other variables that are needed in order to make sure that the state of charge of the battery will stay within limits, like 100% and maybe something like 10 or 5%, in order to not to use too much the battery. Then we also have to make sure that there will be a conservation of energy. So households import and export must be computed, and the battery operation has to be physically possible, meaning that we can't charge and discharge at the same time. So that's why we need some auxiliary variables such as binary variables, which makes the formulation, the problem, a mixed integer problem, problem. And in the work that we propose, so we include the we include the battery lifespan, which is not shown in the convention, which is not usually used in the conventional battery optimization formulation. But so that will be presented in 2 slides. So basically, if we have a look concretely how it works, we have a household with PV or wind turbine and the battery. Then there is a forecast of the electricity price for tomorrow, of the production for tomorrow, and of the demand for tomorrow. And based on that, using the formulation that we just saw in the previous slide, we provide a schedule for the battery, like so we see the state of charge in yellow, and we see all the exports for the following day. So here the battery is exporting when the price of electricity are higher. And when we want to include the cycles into consideration, this is the formulation that we obtain. So we still want to minimize the energy import costs. We still want to optimize the energy export revenues. And we also consider the cycle cost as a cost that we want to minimize. So what we propose in this paper is a formulation that captures this cycle cost even if the cycles are not starting at 100% of state of charge. And we include that in the formulation that is a formulation that optimizes the economic situation of the household. So basically the life cycle has been converted into dollars or euros and is included into the objective function. In terms of variables, so we had to add some variables, and especially we add a cycle depth variable, which is a 24 elements vector if we have 24 time steps. And in each element, we have the depth of the charge or discharge of the battery operation. So if we didn't finish a cycle, the element of this variable will be zero. And if we just finished a charge, then the variable, the element of this vector will be equal to the depth of this charge. So there are many other auxiliary variables in order to make sure that this cycle depth variable is effectively capturing the depth of each half cycle, so charge or discharge. So there are other continuous and binary variables to compute this cycle depth variable, and everything is in the paper. So refer to the paper if you want to have a look at how it's expressed. So in terms of results, we see here on the top graph we have the demand in blue. This is the time in the x-axis. So the demand is in blue, the PV production is in yellow or orange, and the battery operations that result from the optimization are in green. And if we look at the state of charge, and so this is the lower the graph at the bottom. So in light green, we have the state of charge of the battery operation, and in dark green, this is the variable that I mentioned just before that is able to capture the discharge. So this one is just for the discharge of the operations. So it captures the depth of discharge for each cycle. So here we see that it's computed, so it's basically zero all the time, except when there is the end of a discharge. So if we see here around May 18, we can see that we capture two discharge cycles. So there is one starting around 50%, and another one starting around 20%. If we look at May 20, here we have a full discharge cycle without interruption, and we capture this cycle quite well, even if it doesn't start at 100%. So this is an improvement compared to the state-of-the-art methods. However, what we found out is that the computing time to implement this inclusion of battery lifespan into the optimization problem, unfortunately, the computing time is exploding. So if we compare to some heuristic methods that do not use optimization, so the computing time is 0.2 milliseconds. If we use simple optimization for different time horizon, like 12 hours, half a day, or 72 hours, the computing time for the optimization is below 10 seconds. But if we use the battery costs into the optimization as we just presented, then the compilation time explodes and goes to 30 seconds, even if we do the optimization with a time horizon of 6 hours. So this is a big cost for such an optimization. And if we compare the results for electricity bills of households, because we were considering only residential batteries, so if we consider the the benefits for the households using the 4 different control algorithms that are mentioned in the table. So here the graph on the left, we did the computation for a whole year using different battery size, and we computed the bill for the consumer. And we see that in blue, this is the optimization. This is the bill that is achieved by the optimization problem that was proposed in this paper. Sorry. And unfortunately, because the time horizon that we had to take in order to make the computing time realistic, the results that are achieved with this algorithm optimization formulation are not as good as the other formulations. So just because of this time horizon, in order to make the simulation tractable. But if we see on if we have a look at the graph on the right, that's expressed the depreciation cost of the battery, we see that the optimization that is proposed is well able to minimize the depreciation of the battery, but once again, it doesn't show on the annual bill of the prosumer because once again, we had to reduce the time horizon of the simulation in order to have a tractable simulation. So as a conclusion, we have proposed a new mixed integrated programming approach for battery control that takes into account the impacts of the battery cycles. Unfortunately, the computation time is considerable. So we advise people who want to optimize battery schedule for normal use to not use that formulation directly because it doesn't provide enough advantages compared to other previous methods that make it computationally tractable to optimize the schedule of a battery for a long time horizon. So yeah, that's the conclusion of our work. If you have any question, feel free to ask during the discussion session, and you can also have a look at the paper once it's published. Thank you very much, and have a nice day.